All right, welcome back. So last time we put together a basic character driver. You could read from it, you could write to it, and hey, it worked. But let's be real, a real-world driver needs to be a whole lot smarter. So today, we're going to go beyond those basics and really dig into the advanced stuff that makes a driver truly powerful and robust.
So you've got the read and write down, great. But what happens when a program tries to read from your device and there's just nothing there yet? Does it just fail? And what if you need to do something more complex than just moving data? Like, how do you tell a CD-ROM drive to actually eject the disk? Yeah, a simple write command just isn't going to cut it. These are exactly the kinds of problems we're going to solve today.
So let's jump right in with our first major tool for this, IOCTL. The best way to think about this is as a dedicated private command channel for your driver. It's how you send it all those very specific custom instructions.
IACTL, which stands for Input-Output Control, is a system call that's kind of like a secret backdoor for everything that just doesn't fit into that simple read and write model. Think of it like a universal remote, the volume and channel buttons. Those are like read and write. They work on pretty much any TV. But IACTL, that's like those special custom buttons you program just for your TV. One to switch to HDMI 2, another to turn on the sleep timer. It's for all those unique, device-specific commands.
Now, for all its power, IOCTL is, well, it's kind of controversial in kernel circles. The problem is, every single new command you add is basically a brand new mini-system call, and it's often poorly documented. The arguments are just unstructured, which makes security auditing a total nightmare. Because of all this, a lot of modern drivers prefer to handle this stuff through sysfs. But, and this is a big but, IOCTL is still everywhere. It's incredibly common, so you absolutely have to know how it works.
So how does this actually work? How do you define one of these commands? Well, it's not just some random number. It's this really clever 32-bit integer that's broken up into 4 parts. First, you've got a magic number, which makes sure the command is actually for your driver. Then there's an ordinal number for the specific command you want to run. Then a direction, which says if we're reading data, writing data, or neither. And finally, the size of that data. This whole structure is a brilliant way to prevent a program from accidentally sending, say, a format disk command to your audio device.
And here's a fun bit of kernel history for you. This elegant structure, it wasn't there in the beginning. Early versions of Linux just used a plain old 16-bit number. Linus Torvalds himself later admitted, and this is his own word, that it's because he was just clueless back then, and this much smarter system was designed later. It's a great little reminder that even the best systems have to evolve.
So what does this look like in your actual driver code? Honestly, it's usually just a big switch statement. It looks at the command number it received and then just jumps to the right block of code. And, this is critical, for any command that could be dangerous or affect the whole system, you must do a permissions check using the capable function to make sure the user actually has the right privileges, like capsysadmin, before you do anything.
Okay, so we can send commands, awesome. But let's go back to that first problem we talked about. What does the driver do when it can't fulfill a request right away? Well, the answer is, it waits. And this brings us to the whole concept of blocking I/O.
The main tool we use for waiting is called a wait queue, and it's pretty much what it sounds like. It's a list of processes that have been put to sleep because they're all waiting for the same thing to happen. You know the best way to think about this? Imagine you're at a super busy restaurant. You give your name to the host, they put you on a waiting list, and you go sit down. You're effectively sleeping. When your table is finally ready, they buzz you and wake you up. That's a wait queue in a nutshell.
In your code, this magic is handled by a function like waitEventInterruptible. It takes 2 really important things: the wait queue you want to sleep on and a condition. Your process goes to sleep right there, and the kernel won't wake it up until that condition becomes true. And we almost always use the interruptible version, which means the sleeping process can still be woken up by a signal, like if the user hits Control-C. That's super important for a well-behaved system.
And here's the other side of that deal. Somewhere else in the system, maybe an interrupt handler just got new data, or maybe another process wrote something to your device, that condition the first process was waiting for is now true. So that code then calls wakeUpInterruptible on the exact same wait queue. This is the buzzer going off. It tells the kernel, hey, wake up anyone waiting here, and the sleeping process can finally continue its work.
So this sleeping, this blocking, that's the default behavior. It's usually what you want, but it's not the only option. An application can open your device file with a special flag, O_nonblock. And if that flag is set, your driver should never sleep. Instead, if it can't do the job right away, it has to immediately return an error code, -EAGN.
This basically just means, nope, sorry, not ready, try again later. This is absolutely essential for high-performance applications that need to stay responsive.
Now, non-blocking I/O is cool, but imagine just calling read over and over and over again, only to get that negative EAGN error back every time. It's super inefficient, right? What if your application needs to watch dozens or even hundreds of files at the same time? Well, that's where poll comes into play.
The poll and select system calls are amazing. They let a single process monitor a whole bunch of files all at once. Think of a security guard watching a big bank of monitors. Instead of having to physically walk to every single door to see if someone's there, they can just glance at all the screens and instantly know which door is opening. Poll lets an application do the exact same thing with all of its open files. And the best part is, your driver's role in all of this is actually pretty simple. When the kernel calls your driver's poll method, you really only have to do two things. First, you call poll wait, and you pass it any of the wait queues that are relevant. This basically tells the kernel, hey, if something happens on this queue, let that application know. Second, you return a little bit mask that tells the kernel the current state of things. Can you read from the device right now without blocking? Can you write to it?
And that bit mask is made up of flags just like these. Poll in is your driver shouting, hey, data is ready, come and get it. Poll out means the coast is clear, you can write now without having to wait. And of course, there are others for when an error happens or when the device is hung up, which usually means you've hit the end of the file. It's a really simple but incredibly powerful way for the driver and applications to communicate.
All right, we've got control with I/O control, and we can manage waiting and I/O flow gracefully with wait queues and poll. The last big piece of the puzzle is who gets to use the device and when. This is all about enforcing access control policies. And you can implement different strategies right inside your driver's open method. For instance, you can enforce a really strict single open policy using an atomic counter. This is perfect for a piece of hardware that can physically only be used by one process at a time. Or you could go with a more flexible single user policy. Here, you check the user's ID, which lets that one user open the device as many times as they want while blocking everybody else. You can even get fancy and make the open call itself block, putting any new processes into a wait queue until the device is free. And this all brings us to a really fundamental design question that every driver author eventually faces. Should your driver be the one to enforce the policy, or should it just provide the mechanism? In other words, should the driver dictate all the rules, or should it just give the tools to user space programs and let them figure it out? There's no single right answer, and it's a great question to mull over as you design your own drivers. Thanks so much for joining this explainer.